the technology, right? So you have to kind of get that group who needs it to trust more. Okay? And so if you look at this portion, there's clearly a time value for parents. It works really well, right? Parents need that, and the kids will trust the technology, so that should favor adoption. And here, there's a time value for children who have to take their parents. You know, they could then send that car to take care of their parents. So they will, you know, they clearly a time value there. And then at this stage, there's a safety value for parents, right? Because yes, they can drive, but you really don't want them to drive. You know, anything that can push that a little later from a safety perspective is good. And if you look at this part here, there's really a safety value for self, right? Because you know, since your ability to drive is diminishing, you know, there's a safety argument for why you might want a chauffeured, driverless vehicle. And then, you know, that whole range in the middle, of course, is where the usual kind of trade-offs are gonna come in. The case may not be as obvious, but what's interesting is there's typically a cohort effect, fortunately, where trust will be increasing over time. So maybe, you know, the folks who have started here with trusting the technology are not going to have a problem when they're going to be older, because of course they grew up with it. Of course, by then there will be other technologies that they will not trust, but that's another story altogether. Okay? So both an increasing trust effect and then increasing need factor. Okay? And so then, so when you consider the trade-offs then, on one hand, the autonomous car is a mobility tool, which is safer, more efficient, that's going to allow you to multitask, short versus longer time spans, and so on. But really, the nice part of it is you'll have an assistant, right? And who doesn't need that, right? Since, and of course, in other cultures, you know, there are examples one can use. There are chauffeurs, you know, people who, there are drivers, professional drivers, that do a lot of these things for people. Of course, you can't and you do multi sort of. You share the vehicle because, you know, they take one kid and they'll take another kid and they'll go get the, you know, spouse, etc. So there's a lot of that use. Now, but we want algorithms to do that instead, and you know, those are being developed. But that value there of robotic assisted, where a lot of mobility chores that are currently imposed by an auto-centric suburban life can be relieved. And of course, for small businesses, you know, you get your delivery boy, basically. You just send somebody to go deliver, you know, pick up supplies, etc. So if you want to look at adoption propensity in my very simplified world, okay, and so of course, if you are talking to a business school crowd, it's can only have four, you know, 2 dimensions and 2 axes and 4 boxes, right? So we're going to look at it. So you can be money constrained or you can be time constrained. Here, and you can be both, of course. So these are the 2 dimensions, the extent to which you're money constrained or time constrained. And if you are time constrained, but you are not money constrained, then great, there's high value and you can afford it. So there's high propensity of adoption. And if you're in this box, you're not time constrained, but you are money constrained just as well, because you know, you're not going to be able to afford it, right? But you don't need it as much. Okay. Then you have, of course, this portion here where you may not be time constrained, but you're not money constrained. So there is the what Kornhauser calls the bling factor, right? It's a toy, you know, luxury. And then we get, of course, into that portion there, which is probably most of us, right, where we are time constrained and money constrained. And then the question is, you know, there's a role for policy, discounts, incentive, payment plans that are going to be then affecting the kind of adoption that we get. And this is where a lot of the models of shared mobility and so on are also going to be playing. One more of these. This is now health constraint and money constraint. So we take out the time constraint, but we're health constraint. And in this case, you can, again, if you're health constrained but not money constrained, great, high value, you can afford it, high propensity. If you are in the money constrained but not health constrained, great, stay healthy, right? And of course, if you're not health constrained and not money constrained, then we go into the time value, the convenience, the safety angle. And health constrained, money constrained, a lot of people. Their role for policy, that's your Bernie Sanders kind of box, right? Okay. So let's talk about planning models here. And so one view, and I think it was either Ram or John Walker who had organized a session at one of those conferences, is how good are our planning models to deal with autonomous vehicles? And so we kind of build it up. So let's take I sort of went back to Transportation Systems 201, Martin Mannheim's book, in terms of you have demand, you have supply, you have activity, you have the technology. And so the incremental view is to say, well, driverless vehicles have different performance characteristics. They enable different service levels for a given infrastructure. So you come up with the appropriate supply models and you replace them in your typical tools, and you can simulate them. And so the system performance will be dependent on these technological features, which you can simulate, generate the models, and update all your supply side. And in terms of the behavior side, you have the same models, the same attributes, the level of service attributes that typically affect the travel behavior in our models. Things like travel time, reliability, these are the usual ones. But then there are some less usual ones: comfort, perceived safety, availability, fixed waiting time, in addition to cost. And our travel behavior models are supposed to capture responses to these attributes in terms of traveler choices of destinations, modes, and routes, though really the whole activity scheduling, rescheduling with fewer constraints is probably beyond this incremental capability. And then an incremental view is to then iterate these with kind of tweaking essentially the performance models and our behavioral models slightly to be able to address that. And so again, your performance models are affected by, they give you, for a given technology and certain level of demand, we'll give you the typical attributes, the performance measures, as well as things like availability, comfort, convenience, safety, etc. And on the demand side, we have our usual activity choices and travel choices. You tweak the performance models for autonomous/connected vehicles, and that gives you different performance measures that you can then feed into your pretty much same demand models, and then change the flows, and you iterate that. And that's a very incremental view of things. But the other thing that one absolutely needs to add, though, is the technology features then become vehicle attributes that will influence vehicle type choice in possibly the same way as fuel type or different performance features. Again, that's all part of the incremental view. And so you kind of add mobility choices, a vehicle type choice, that is degree of autonomy, and possibly a mobility program choice that you include there. Less incremental, though, is to recognize that there will be major activity shifts and mobility use. And we talked about the two key aspects there of the autonomous car as mobility tool and a robotic assistance. And then the implications on the demand side would be for vehicle use and sharing within the household, the whole chauffeur features of waiting or showing up when needed, additional trips in VNT that may be introduced into deadheading, remote parking, and so on, and the whole aspect of sequencing and routing within the demand side. And on the supply side, issues of vehicle availability in shared vehicle type situations. And the second set is really more major mobility supply shifts. And if you look at what Uber is trying to do now with driverless vehicles, what Ford is trying to collaborate with, there's all sorts of things, discussions that are going on in that sense. And if we're seeing this already, just imagine what you will see when these things are even more real and with us. And so if we then want to look at that in this context, that's really introducing a whole new layer of activity system and mobility choices that our current models do not really handle and cannot simply handle just by tweaking. And similarly, you have the whole supply side that is in terms of supply of services, where there's sort of a whole set of new mobility industry supply options. That's the second one that will then affect the technology. And it's these two levels where our tools are quite deficient. in fact, and where you know we say, well, how would we approach this methodologically? Okay, and so really to do number two, which is harder because you can't just predict the emergence of that from anything that you see historically. You have to take the view of an entrepreneur, essentially, of somebody who is trying to offer a service and then imagine certain scenarios that may be offered. So you have one that is kind of, you know, more of a social good type shared vehicles, one that may be more of an elite with different types of availability. So I have a PhD student now who's looking specifically at algorithmic aspects of autonomous vehicle sharing. Okay? Under different cases. In one case, you may be doing subscription. Other cases, it's by the ride, like in Uber today. Other cases, it would maybe I just want it for a certain slot of time that is totally allocated to me, and during this time, I don't want it to go to anybody else. So there's all kind of options like that, and he's developing algorithms for all of these different formulations that you could then run online to do that. Okay, so whether that's appropriate in the context of a planning tool is not clear, but that's kind of, to me, the first approximation added is to put yourself in the you know, the shoes of somebody who may be providing the service, and then create scenarios on that basis. On the behavior side, these as a, you know, as a kind of have summarized that you know, in terms of our tools, that the flow modeling aspects require additional calibration, but that's the easy part, I think, today. But as I was saying, on the behavior side, there's more uncertainty. And the way to address that on the behavior side is really to go back to basics of travel activity behavior research, combining qualitative insight with experimental methods. And there is really no escape here than to sort of create experiments, meaningful experiments that can help us gauge how people will interact with different options and different alternatives, because the incremental scenario is just not going to be enough. Okay? So the summary there is that existing models are not up to the task of modeling the full implications of these new mobility supply scenarios. Okay, flow implications, and I really want to get to this. That's a good point. All right. So this is based on work was done in collaboration with a recent PhD student, Larissa Talibpour, who is currently at Texas A&M. And essentially, we asked the following question. Clearly, we're not going to go from one day to the next into autonomous or autonomous connected or connected not autonomous. It's going to be, you know, we're going to have different vehicles in the traffic mix. So how do we address that, and what can we say already from what we know about what the implications might be for stability, for throughput, and so on? So we took a micro perspective here. We went and simulated at the micro level the choices that drivers make. And this is not a driving situation, not a travel behavior, but just driving choices. And of course, the two main choices when you're modeling drivers microscopically is acceleration choice or car following and lane changing on a highway. Those are the two main decisions that you typically will model. You could embed that in more complicated things of trajectory planning and things like that, but at the most basic level, it is following. And we simplify things, which is, it's a straight, if you take a straight highway, then there are no other decisions to make. Do I exit here or not? We're not doing this yet. Just very simply, now looking at just the acceleration framework in car following. And so 3 cases: no automation, not connected; no automation, connected; and self-driving, but not connected. Now you could say self-driving connected, that's another one, but really most of the insights you're going to get already from the not connected aspect of it. And so for each one, we kind of formulated the corresponding behavioral models. And so for no automation not connected, you have the whole literature that's available. And in fact, my group has been working on a kind of more behaviorally rich framework that considers the risk trade-offs that drivers have and so on, that have been calibrated, published, etc. with real data, mostly NGSIM data, which Federal Highway had collected. But we kind of took that whole machinery and put it on this side. Okay? for the no automation, not connected. And we did not put in things like the driver that is not connected nor automated, recognizing that this is a Google car who is safer than he or she is, and therefore will try to cut in front of them. We did not put that behavior in there. Okay? We're just assuming that they drive the same way they see another car. Okay? And they are reacting and responding in the same way. And when it came to no automation, there's different sub-cases here with whether it's only V2V, V2I, and with one or the other. But mostly, the main model that we use is called the intelligent driver model that was developed by Treiber, Haneke, and Helbing, and further developed by Kesting, who worked with Helbing at TU Dresden. The intelligent driver model is a acceleration choice car following model that tends to be a little less behavioral than typical models. So it has been used, for example, by BMW to examine the impact of automated car following. Okay? And so it does two things. It reduces the reaction time a little bit, and it makes the sort of sensitivity less brusque. Your behavior less brusque than you might do it as a human being. And I should mention with the regular drivers, yes, we have heterogeneity in there because there's different types of drivers, and we have calibrated that very carefully to have different types of drivers with different parameter values that are consistent together. And when we generate them from correlated distribution. So it's a good piece of work on its own. But this here is bringing in now the intelligent driver model as the current sort of most appropriate model here, and you could make it more or less sensitive by tweaking some parameters in there. And when it came to the self-driving portion of it, well, really there it is. It's robotic pretty much. So the algorithms are driving it. The the typical thing here is to assume 6 sensors with the field that they're covering, and then we use the model from the literature that primarily Bart van Arem and his group at TU Delft had been using, that essentially determine the acceleration so as to maintain the speed to maintain a certain distance that is safe to brake at that particular speed, and it does so with very little latency in terms of sensing what the vehicle in front of you is doing. Because that's the whole thing. With human drivers, there's always that reaction time. And here, you're cutting out that, and you can change the latency, but pretty much given that, the application of the acceleration becomes automatic. Okay? So that's what the robotic capability there. And so we implemented something in here. Of course, the question that I usually get on this, but BMW does it differently, Infiniti does it differently, which did you test all of those? And no, if they give us their algorithms, we can then put it in there. You could bring a black box and put it in there. As long as you have the same inputs, it will produce the acceleration, and then you can simulate. Okay? But we did not attempt to guess what Ford is doing or anybody else. Okay? So now, one other thing that's important with connected vehicle technology is really the communication side. We found ourselves becoming wireless communication modelers because we were modeling the way the messages were being transmitted. And we have to do that jointly with the traffic flow because, again, the ability of different strategies to be implemented depends on the messages being communicated. And so we collaborated with one of our faculty at Northwestern, who's an expert in ad hoc wireless networking. His name is Fabian Bustamante, though Ali Reza did most of the heavy lifting with that. And we found that most of the previous studies made assumptions that really are not appropriate for traffic. As the wireless communication folks did not specifically develop the kind of capability that recognize how traffic may be changing. For example, they assume that the road segments are all one-dimensional objects. Okay? When you have multiple lanes, that's not the case. They assume that speeds are normally distributed, may or may not be the case, especially when you have stop and go and so on. It's nothing like being normal. You have all kinds of bimodalities and so on. And the whole notion imagine that you have a homogeneous Poisson distribution of vehicles over space also does not work. So, so we just simply illustrated that. Alireza got the actual traces of the vehicles from NGSIM, t equals 0, t equal 100, t equal 500, 1000. You can see it's not a single line, there's multiple lines. The distribution is changing. So a lot of those assumptions actually do not hold. So we went in and we found a theory called percolation theory, which is applied when a fluid is spreading through a medium or a disease is spreading among people, information spreading in social networks, liquid penetrates in a porous material, which has been used in this context. And then a lot of it is about forming clusters of vehicles. So ultimately we ended up getting in the business of forming clusters of vehicles because it works this way. Okay? When vehicles are moving, one of them is actually acting like a base station, like the baseband, and the others are communicating with that vehicle. That vehicle may be communicating with other clusters or may be communicating with the infrastructure, but not everybody is getting that communication. And they're getting it only from the cluster leader, basically. And so the size of the cluster is going to be affected by the power that you're using, that is available, and that affects the package, the sort of package delivery rate, essentially, which could be as low as 50%, but you want it to be close to 100. So there's different trade-offs. You want more delivery of that message, you need more power, and so on. So we worked with that and then found that the clustering logic that is being used was also not great, because typically you say, all right, we're going to take vehicles that are in some neighborhood and cluster them. That makes sense, but vehicles are going at different speeds, so that cluster is going to then separate out and so on. So we kind of want to